Okay, so we get into the core of physics, and as you can see, it's called Newton's laws. Now, there are 4 laws that we are going to look at when it comes to laws of physics. How many?
4.
Beautiful. We are going to go into 4 laws. All right. Let's start with the first law, Newton's first law of motion. Newton's first law of motion. Now, we must be able to state the law, understand the law, and then apply the law. So 3 things: state, understand, and apply. Now, what is yes, we have to state, understand, and apply. So let us state the law. What does Newton's first law say? It says an object will remain at rest or continue in uniform motion. The word uniform motion, we can also use the word uniform velocity. Unless acted on by let me clean that, by a non-zero. The word non-zero means it's not equal to 0. Resultant force. An object will remain at rest or continue in uniform what? Motion, unless acted on by a non-zero force, resultant force. So that is us stating the law.
Yes.
Let's try to understand the law. If you put your book on the table and nothing touches it, no one is moving it, do you know your book will remain there forever?
Yes.
That is what the first statement says. An object will remain what? At rest.
Yes.
So if no one is taking your book remains where it is. So the object remains at that position. But now, let me give you an example of understanding the law. If you get into a car and the car is stationary, right? The car is not moving. It means everything in the car is also what? Not moving. Good. When the car starts moving, what happens to you? You are also going to move. Yes. But do you notice that you move, it's as if you are moving backwards first before you move forward? I'll give you another example. That would make sense. When the car is moving and we stop the car, what happens to you?
I stop.
No, before you stop, you move forward.
Then I stop.
Good. That's the same thing that when the car starts moving, you also go back before you start moving. Yes. That is Newton's first law. Why? When your body is stationary, your body does not want to change position until there's a force that pushes you.
Which is a force applied.
Now, okay, yeah, kind of. A non-zero resistant force. That's why also when the car is moving and we stop the car, your body wants to continue in that state.
Yes.
That is Newton's first law. That the object will remain at rest or continue in a state of what? Uniform motion. Unless acted on by a non-zero force. Example, an object stationary wants to remain stationary. Likewise, a moving object wants to keep the motion. Even when forced to stop. So do you understand it now?
Yes, I understand.
Okay. Now we look at a word called inertia.
Oh,
Why is she laughing now? Why are you laughing?
I asked you many nations, but no, that.
I don't know it. I'm just going to ask Google now. So what is inertia?
I don't know.
The property of an object to resist change. And that's what I was explaining when I said example. So an object is moving forward. When we stop the car, what happens? The object still wants to continue what? Moving. That is called inertia. The property of an object to resist what? Change.
Change.
Or we call it resistance to change. The bigger the mass, the bigger the inertia. I'll explain something very simple to you. The bigger the mass, the bigger the what? Inertia. If you remove, let's say you are in the you from school right now, you put your bag, all right, on the seat of the car. But then you pick your water bottle and also put it on the seat. Which one is heavier?
My bag?
All right. When the car stops, let's say it stops suddenly, it's easy for the which one to fall down? Is it the water bottle or the bag? Good, because it's lighter. It has a lower inertia. It has a lesser resistance. So the bigger the mass, the bigger the what?
The
Inertia, which is what?
The property of an object to resist, which is my bag.
The resistance to what? To change. So a bigger object will have more resistance than a smaller. So a smaller object can easily change. Let me give you another example. Let's say you're driving in a car, all right? And let me do this. So that's the road. The car drives this way, right?
Yes, sir.
And then the car turns this way.
Uh-huh.
Do you know that your body is going to hit the car? Well, let's say you are sitting in front of the car. All right? That's the car. When the car turns this way, your body is going to actually hit the side of the door as if you want to go out.
Yeah.
Do you know why?
Right?
Your body, at this point, your body is moving this way. Your body still wants to continue that way.
Oh.
Make sense?
Yeah, makes sense.
That's why when you put something on the car at the back of the seat, when the car turns, you see that thing rolling as if it wants to continue in the original motion.
Yes.
That is called inertia. Because it wants to stay and not change direction. Make sense now?
Yes, sir.
So the bigger the mass, the bigger the inertia. Are we done there?
Yes, sir.
Make sense? Lovely. So if you get into a bus, that's why when people get into a bus and the bus stops, what happens? Everybody collides with each other. Brrr. You've experienced that before?
Yes.
Good. It's called inertia. So I have stated, we have understood, and we have applied.
Yes.
We're good?
Yes, sir.
Lovely. Newton's second law. We are going to state the law quickly. Then we are going to talk about forces. We're going to describe all the forces we have. Newton's second law states that when a net force acts on an object, the object will accelerate in the direction of the net force. Acceleration is directly proportional to the net force and inversely proportional to the mass. Are you writing quickly?
Yes, sir.
Write as quickly as possible. The bigger the force, the bigger the acceleration. Bigger the mass, the smaller the acceleration. Therefore, F net equals to MA. Sum of all forces acting on an object. Mass measured in kilograms. Acceleration. The rate of change in velocity, and the unit meters per second squared. Okay, write quickly. Let me know once you are done. Holler at me when you are done. Yes, Bonolo?
Your screen went blank, actually.
My what?
Your screen,
What's wrong with my screen?
it went blank.
No, it's on your side. Try to check again. My, huh?
Maybe.
Yeah, it's on your side, not this side.
Yeah, for sure.
It's fine now.
Yeah.
Okay. All right, so if you look at, we said when a net force acts on an object, the object will what? Accelerate in the direction of the net force. The acceleration is directly proportional to the net force. What does that mean? It means when the net force is big, the object will move faster. So when you push, it's like pushing an object with so much force. The object is going to move quickly, right?
Yes, sir.
And it's inversely proportional to the mass. It is easier to push a light object than to push a heavy object.
Yes.
And our formula would be F net equals to ma. F net equals to ma. What is F net?
This is sum of all the
Good.
on an object.
It's like talking about your F resultant.
Yes.
All right? And the unit of force is newtons.
Newtons.
Unit is newtons. And we write N. Mass is measured in kilogram. And what is acceleration? It is the rate of change of what? Velocity. All right? Rate of change of velocity. You must know that definition. A is change in velocity over change in what? Time. We did that in grade 10. Change in velocity over change in what? Time. Are we good?
Yes, sir.
Now quickly, let us jump into this thing that we call forces. Let's look at forces. Quickly. Forces. We are going to look at different types of forces. We're going to look at 5 of them. All right? Then when we add them together, we get F net. Forces. Number 1, normal force. Now there are so many ways of representing it. We can use Fn but I like Fn. Fn makes more sense, right?
Yes, sir.
So let's stick to Fn. Normal what? Force. What is normal force? That's the question.
Should I answer?
You know it, talk to me.
Well, normal force is the force that is, I don't know, opposite to the gravitational force.
Yeah. You are lying, child.
But Mr. Fiona.
No, Mrs. It's not the one. It is the force exerted by a surface. All right. You have an idea, but I need you to give me the exact definition. The force. All right. So I'm giving you the definition now. And with physics, you know it. You must give me the exact definition.
Can I say something?
Yes.
You define inertia. You are not defining force. I was given a homework. And come back with the definition.
Of what?
Of all the 5 things.
Of what? 5 things.
Of inertia, normal force, frictional force, static frictional force, and then stating the Newton's first law.
All right. I'm sure by the time I'm done, I will have answered all your questions. I have already answered 2.
Yes.
I have answered inertia. I've answered Newton's first law. Okay, so let's continue. By the time we are done, we should have answered all your questions. All right, so normal force is the force exerted by a surface on an object, and it acts perpendicular to the surface. When we say perpendicular to the surface, it means it acts at angle of what? 90 degrees. So for example, if I have a surface like this, my normal force will be acting that way. And this angle here is what? 90. So that's going to be my surface. And that is going to be my normal what? Force. Now, what if my surface is like this? How will my normal force be acting? It is still going to act like that. Because this must always be 90 degrees. So that is my normal force. And this will be my what? Surface. So it will always act in that direction. Now look at this. What if I have this? Surface like that. It must still act like that. Because it must be at 90 what? Degrees to the what? Surface. Are we on the same page?
Yes, sir.
All right, beautiful. Normal force is a contact force. The word contact. What does the word contact mean?
Touch.
It must touch. Good. It means object must touch the surface. So if there's no surface, no normal. That makes sense, right?
Yes, sir.
All right. We are done with normal force for now. We're just quickly looking at all the forces. Number 2, applied force. We are going to say F at. This is a push or a pull. Make sense?
Yes.
If I'm applying, it's either I'm pushing or a pulling. It is a contact what? Force. You cannot push something you are not touching. Make sense?
Yes.
So if I'm pulling something, I must be touching it as well. All right. Number 3, tension. Have you heard that before?
Yes.
We are going to call it Ft, or we can say T. It is the force in a rope or a string. It is a form of applied force. It is a contact what? Force. Quickly write all of this for me. Hi, Bonolo.
Hey, sir.
Sorry, I didn't leave you behind. I was just quickly a call came in, so I was just attending to it quickly. All right. So weight. We're looking at number 4. Weight. Weight is the pulling force of the earth on the object. Another word that this is called gravitational force. So that's the other word. So the earth is pulling all objects to itself. That force is called the weight, or the gravitational what? Force. All right. So if we say gravitational force, we would use the word Fg. That's the symbol, which is the same as the weight. So it is the pulling force of the earth on all objects. It always acts vertically downwards. Always. So the weight is the same as the Fg, which is equal to m times g, where m is what? Mass measured in kilogram. And what is g? It is gravitational acceleration. Yo. And this g is 9.8 meter per second squared downwards. So g is it's always acting vertically. Please take note of that word. It acts where? Vertically what? Downwards. So if I have an object, let's say I have a box. If I have a box, this force is going to be acting vertically, means straight down. Fg, and it's from the middle. Even if I have this object on an inclined plane, so let's say we have an object on a plane. All right, like that. You can imagine that, right?
Yes, sir.
The object is on the plane. How will my gravity be acting? It's going to come from the center, and it's going to be vertically what? All right, vertically what? Downwards. It's not going to bend, it's not going to do anything, it's just going to be like that. So if I have this up surface again like this, I have this from the center again. So it is acting from the center, and it acts vertically what? Downwards. So it is the force of the earth on an object. And the earth is always pulling all objects what? Downwards. Are we together?
Yes.
Okay. Are we done writing?
Yes, I'm done.
So fast.
I was drawing when I was done.
Oh, okay. Number 5, frictional force. Number 5, frictional what? Force. So when it comes to frictional force, we are going to talk about 2 types of forces. When it comes to friction, we are going to talk about 2 types of forces. All right? But generally, friction is a force that opposes motion. But we're not going to define it like that. We are going to talk about 2 types of forces, frictional forces. All right. Number 1A, we are going to talk about let's talk about static kinetic friction, or static frictional force. Static what?
Frictional force.
Frictional force. I'm going to use small f and s to represent that. Static what? Frictional force. Now, what is the definition of static frictional force? One second, just this mic cable. Let me just fix it quickly. Okay, can you hear me?
Yes, sir.
All right. Static frictional force. This is the force acting parallel to a surface, and it opposes the tendency of motion of a stationary object. The object is not moving relative to the surface. You must remember all of this definition. So when we put an object on a table or on a surface and the object is not moving, what is keeping it is called static. Static means stationary. So this is a force acting parallel to a surface, and it opposes the tendency of motion of a stationary what? Object. The object must be stationary. Then we are going to look at maximum. I'm going to demonstrate this for you maybe next week. Maximum static frictional. Maximum static frictional what? So all of these forces is what is going to make F net resultant. All right?
Yeah.
This is the maximum static frictional force just before the object starts moving across the surface. I will explain that. I wish I could quickly demonstrate that with you. Kenna, let me demonstrate that for you quickly. Tell me when you're done writing. Just need to get that. Actually, okay, let me get the app for you. I want you to see what's going on here. So I'm just quickly going to get an app. Make sure you keep an eye on my screen. All right, keep an eye on my screen. Can you see my screen though?
Yes, sir.
All right, beautiful. I want to demonstrate the static friction for you and the kinetic friction. Almost there. I hope I can find it quickly. One second, where are you? All right, it's just loading up. Okay, while it's almost done, I wanted to continue. All right, so we're talking about friction. Let's look at friction. Good. Look at it. So this object here is stationary, right?
Yes, sir.
All right. Okay. Because this object is stationary, it doesn't mean that there's no force. There's normal force, right? Why is there normal force? There's normal force because it's on the surface.
Yes.
Number two, what other force do you see?
The gravitational force.
Beautiful, because it's been pulled down. All right. Now look at, there's also frictional force. I want to push. All right. Can you see the word friction?
Yes.
Good. This is called static what? Friction. Why? The object is not moving as at yet. All right. So it's static. Now look at, the more I push, the more the static friction increases. Check. Can you see?
Yes, I can see that.
And the object is not moving yet, right?
Yeah.
So the more I push, static friction increases. But we are going to get to a point. Let's continue. Can you see that it's increasing? But I'm pushing. My applied force is increasing. But this object is still not moving. Oh, but it's now moving.
Yeah.
Okay, I need to get back to where it stops moving. All right, let's go back again. Just before it starts moving, just before, take note. Can you see it's increasing, right? Friction is increasing. We are going to hit maximum shortly, and after maximum, the object starts what? Moving. Oh, that's it. Did you notice that part?
Yeah, I think I do.
Okay, check again. Because there's something I'm going to come back for you to see here. Not moving yet. It's increasing. I want you to look at that red. Can you see the red arrow?
Yes, sir.
It's going to decrease just when it starts moving. Look at it. Can you see it's now smaller?
Yeah.
And the object is moving. Let's explain that. So let's quickly put an explanation. As applied force increases, on a stationary object, the static friction also does what? Increases. Until it reaches what?
The maximum.
Beautiful. Okay, this one is going to be written as, let's put the symbol, Fs max. Until it reaches maximum what?
Static friction.
Maximum static friction. Then the object starts what? Moving. Object starts moving. Then we look at the third one. Kinetic frictional what? Force.
What?
We're going to write it as what? Fk. The K stands for kinetic. The S stands for static. Makes sense, right?
Yes, sir.
All right. So what is my kinetic frictional force? It is the force acting what? Parallel to a surface and opposes the motion of this time around, moving what? Object. Relative. So when we talk about kinetic, we talk about moving. When we talk about static, we talk about what? Stationary. All right?
Yes, sir.
Static, stationary, kinetic, moving. It is the force acting parallel to a surface and opposes what? The motion. Please take note, this is very key. Opposes motion. Even this one opposes the tendency. Can you see the word tendency?
Yes.
So if I'm pushing to the right, I want the object to move to the right. It means friction must be acting to the left. Are you done writing?
Yeah.
Check this. Let's go back to that thing. Do you see? I'm pushing. Can you see where my friction is?
Yes.
I'm pushing to the left,
When it's going to the right.
but this friction is acting where? To the right, because it's opposing the direction of motion.
Of the motion, yes.
If I start pushing from here, hey, when I come this side, man. Hey, don't fana. Yeah. Hey, when? This guy. Stop on Kanjan. Hey, Mona. Okay. All right, let's do this. Aibo. Aha. So if I push to the right, I want this object to go to the right. Can you see that friction is acting to the left?
Yes, sir.
It's not opposite applied force. I didn't say opposite applied force, right? It's opposite the direction of motion. So if this object is moving to the right, friction is acting to the left. So take note of that. It's in the direction of, opposite the direction of motion. So when we start drawing, we're going to ask whether we are moving to the right or to the left. All right. I think I've answered all your definitions. If you notice, okay, you owe me chocolate. Next thing, coefficient of friction. Coefficient of friction. It's called a mu. Mu. And there are two of them. We would have this, which is coefficient of static friction. Once I say static, the object is not
Moving.
all right. And then we have that with a K. Coefficient.
Kinetic
Oh, beautiful. Kinetic what?
friction.
All right, but what is coefficient of friction in itself? This defines the degree of roughness of a surface.
Roughness.
Yes.
Oh.
So rough surfaces have friction. So whenever you see in a question the examiner mentions the word rough, it means they're talking about friction. Smooth surfaces don't have. They don't have friction. Smooth surfaces have little or zero what? Friction. So friction allows us to walk. The reason why we can walk is because the road is rough. That's why if we pour water on the ground, the road becomes smooth. You fall down. If you put grease on the ground and you step on it, what happens? You fall.
What?
Grease.
Oh, yeah.
Why? Because the surface is now what? Smooth. So rough surfaces have what? Friction. Are you there?
Yes, sir.
Okay. How then do we calculate this coefficient of friction? We can calculate coefficient, the mu s or the mu k, by saying Fs is mu k times n. Where this one is what? Static. Oh, sorry. This one should be S. Not. I can't mix X and K.
Okay.
What is this?
Coefficient of static friction.
All right. What about N?
This is normal force on Newton.
Yes. Normal what? Force. Normal force. Static friction here. Similarly, Fk equals to what? Mu kn. All right? Lovely. The coefficient of friction has no unit.
Oh yeah.
Why?
Yeah? How?
You said, oh yeah. Why?
Right. I was like, oh yeah, but I was like, why?
Because it is a ratio of forces. I'll explain to you now. Ratios don't have units. Yeah. So check something. If I say Fk equals to mu Kn, it therefore means that mu K is Fk over what?
Over N.
Remember what this N is. This N is what? Normal. How do you measure kinetic friction? You measure it in newtons. How do you measure normal force? It's also measured in newtons, the units.
Oh yeah.
So what is newtons over newtons?
Okay,
Good. That's why it has no unit, because it is a ratio of forces.
It's a ratio of forces.
Yes.
The coefficient of static or kinetic friction has no unit.
Because it is a ratio of forces. Another point quickly. The coefficient of friction of a surface remains constant.
Remains constant.
Yes. It remains what? Constant. Therefore, because it is constant, frictional force is directly proportional to normal. And Fs, do you know what this means? This means the bigger the normal force,
the bigger the frictional force.
The bigger the frictional force. The bigger the frictional what? Force. Since coefficient of friction is constant. Since the coefficient of friction is constant. We are pushing today. We are pushing. Tell me when you're done.
No,
You are screenshotting.
yes.
Hey, wait, Nana. Laziness, lazy bum, lazy.
But you said you were tired.
No, we are working, Nana. Siyasebenzala.
What do you mean by orange food? So yeah, that's right.
Okay, just do you, boo.
Yeah?
No, let's continue. Just tell me when you're done.
I'm done.
Ah, that's why you were taking pictures. I thought you were writing.
Oh no, I only took picture of this page. That page only half.
Okay,
The
Bonolo.
rest of written half.
Okay, Bonolo, don't fight me, ne?
So,
Don't fight me. I'm just saying. But it's okay, I understand. So we have a graph. We can have a graph, and we would have static friction and normal. Because we said it is what? They are directly proportional. We are going to have a graph like that. Wait, I think I'm putting this wrongly. I should put N here, Fs there. That as the normal force increases, the friction also does what? Increases. Directly proportional again, my graph must start at the origin.
Okay.
The gradient of the above graph, do you know how to get the gradient? Huh?
I forgot.
Okay. The gradient of the graph is called the coefficient of friction. Gradient is change in y over change in x.
Y2 minus y.
Yes, that's the one. Gradient is going to be coefficient of static friction here. The gradient will be coefficient of kinetic. Because it is change in y over what? Change in x. Because we are saying m is change in y over what? But what is on the y-axis? Static friction. What is on the x? Normal. And this is static. The same thing. Are we good? Are we okay, Bonolo? Hello, can you hear me? Can you hear me, Bonolo? What's happening to my sound? Testing 1, 2. Testing 1, 2. Can you hear me, Bonolo? Something just happened now. Hi, Bonolo. Can you hear me? Can you hear me, Bonolo? Can you hear me? Let me check my sound. What's happening here? Hello, Nana. Can you hear me? Hi, Gavin. I didn't see when you came into class.
Sir.
Hi, Bonolo. Can you hear me?
Yeah.
Okay, I don't know what happened. You just disappeared. Gavin. Gavin, how are you? I'm okay. I didn't notice when you came into class. There's a lot that you need to catch up on. All right. Okay, so we have looked at all the forces We have looked at all the forces. Quickly, free body diagram versus, let me say versus force diagram. This is very, very important. Free body diagram versus force diagram. For a free body, okay, let me force. Let's see if we can use a table form. For a free body, we use a dot to represent the object. We use a dot to represent the object. Given, can you still hear me? Okay. For force diagram, we use a box to represent the object. Forces are drawn touching the dot but pointing out in the direction of the force. Forces are drawn at the point of action from the box. And finally, all forces should be labeled. This one is common to both of them, with full names or symbols with a key. All forces should be labeled with full names or symbols with a key. So we are going to look at a few examples of free body diagrams tonight. Given, let me know once you are done here. I don't know what's went wrong with Bonolo's line.
I'm here.
Oh. Sorry?
I'm done writing.
You are done writing or you are done taking pictures?
I'm done writing.
Given, let me know when you are also done. Okay. All right, so we're going to look at a few examples. We're going to draw free body diagrams. We're going to draw force diagrams as well. All right, free body diagram, force diagrams. Let's look at examples and see how these examiners ask these questions. So I'm just going to quickly grab one question for us to see. So we are doing Newton's laws right now, and it will be tested in grade 12. So if you can see my screen, I actually went to a grade 12 paper. All right, I went straight to a grade 12 paper because it will be tested again in grade 12, so that you can see the relevance of what we are doing, and don't say, now I'm going to cram pass and forget. Nope, doesn't work here. Oh, beautiful. This is one of them. Okay, Newton's laws. This is Newton's laws. Newton's laws. Beautiful. Beautiful. All right, so that's what your question would look like. Let me pick one from, let me quickly also show you one from a grade 11 paper. Let's see this one. Oh, we did this one. Oh, nice. Nice. Look at this one. Let's play around with this one. Let's see if we can get 18 marks here. Can we try this one tonight? Just one? Don't worry, I'm the one doing it. All right? But I will take you step by step. Let's try this one tonight as we just see what these examiners, how they ask their questions. So follow me. It's very simple. I'll show you what to do. Please, just follow me. We're going to do so many examples next week. After this one example, we will shut down the class. If you can keep your mics on for me, I want us to go forth and back. All right, keep your mics on. 2 blocks of masses 5 kilogram and 2 kilogram. Please always read with the diagram. Oh, that's my 5 and that's my 2. Are connected by a light inextensible what? Let me see if you are here.
String.
Good. And in our notes, we spoke about the string. There's a force in a string. What force is that? Go back to your note. There's a tension force. The tension force is the force that you find in a string or a rope. I think number 3. Check. Force in a rope or a string. So immediately I see the word string, I know that there's a force there, which is called what? Tension. So I'm going to underline that. All right. Now, when I say masses, I know this object will have a force of what? Gravity. Right? Mm-hmm. Now, read on with me. A force F is what?
It's applied.
Good. That is telling me there's an applied force. Applied.
There's force applied.
Yes, there's force applied. It's applied on the 5 kg. Can you see that it looks like we are pulling this force here? We are pulling the object at an angle of what? 20 to the horizontal. And the system of the blocks accelerates. In which direction? To the right.
To the right.
So it may, I don't know if it makes sense. We are pulling this object and it's all moving in this direction to the right. As shown in the diagram below. A is equal to what? 2 meters per second squared. The kinetic frictional force, on the block, on the 5 kg block is what?
10 meters.
Beautiful. What type of friction is it? Kinetic. That tells us the object is what?
It's moving.
Moving. All right. Look at 3.1. That you must remember. Define the term normal what? Force. I gave you that definition. It is the force exerted by what? The surface on the object, and it is perpendicular to the surface. That was force number 1. Check. Answer number 1 is done. 2 marks. The force exerted by a surface on an object, and it acts perpendicular to the surface. I'm done with the first one. Easy peasy. Do you see that, right?
Yes.
Easy peasy. That one is done. We're not going to waste time. Just need to practice. Draw what? What are we drawing? A free body. Now, acting on the 5. How do we draw a free body diagram, my good learners? We use a dot. So what forces can we see?
You can see the force, normal action, gravitational force.
Okay, because of the masses, gravitational force is always acting where? Downwards. So we call it the force of gravity. What other force do we see?
Normal force.
Why is there normal force?
Because of
this
on the surface.
Yes, this object is sitting on a surface. So we have what you call normal force. Next.
We have force applied.
Good. You can see the force applied. That F in that direction. Force what?
That's right.
Now what else?
We have a tensional force because of the strain.
Yes. There's a rope here that is connecting these two objects. That string tells me there's what? Tension. Now I want you to listen to how I'm going to do my tension. Do you notice that the 5 kg is we are using the 5 kg to pull the 2 kg. But the 2 kg is also pulling. If we remove this force, do you know it's possible for this object to go down?
Yes.
So it means the 2 kg is pulling in that direction. And that force is called what?
Tension force.
Tension force. But hold on. Look at the last statement. The examiner says the kinetic what? Friction. On the 5 kg. What do we know about friction? Friction. Yes? Go ahead.
You know that this is a force that is acting parallel to the surface.
All right, parallel to the surface, and it opposes the direction of motion. How is this object moving? This object is moving to the right.
By acceleration of 2 meters per second.
Good. If this object is moving to the right, it means friction is acting to the left. That's what we say. That's what we mean. So object is acting to the right. Friction would be acting where? To the left. Guys, your lines must be parallel to each other. So what you can do is we can make the circle what? Bigger. Make the circle bigger. And what is this? Frictional what?
Force.
And you are done with 5 marks there. Very easy. This one is the 5 kg, right? Let's try something quickly. On the 2 kg, what forces do you see? First, it's a dot. Okay, because of the mass, all of this would have what? Force of? All right. Now, what other force do you see?
Tensional force.
Do you notice that that rope is pulling this object up? Up. Can you see my arrow?
Yes, sir.
Good. And that force in a rope is called what? Tensional force. Which other force? Let's check. Is there normal force?
Let me see.
There is no normal force. Why? This object is not touching a surface. Yes. So if there's no surface, there is what? No normal force. Is there applied force? Do you notice that F is only on the 5, not on the 2?
Yeah, it's on the 5.
It's not on the 2. This F is only on, this F is only on the 5. It's not on the 2. So it means these are the only two forces that are acting on the 2 kg. Very important, people. Very, very important. Are we okay?
Yes, sir.
Given?
Yes, sir.
You came a bit late. Have you done this at school? Have you started this at school?
We're not at this part, but we started Newton Law.
All right. Please, my boy, tomorrow Friday, you need to watch this lesson.
Yes, sir.
Please, please, please. Newton's laws, like I told you, will be there in grade 12 again. All right. And systematically, I want to take you through. Now, let's look at this question. The examiner says calculate the tension in the string. Oh, wait. This is now Newton's second law. Our main formula is what? F net. Our main formula is that. F net equals to ma. What does F net mean, by the way? The sum of all the forces. Please, I want you to get me here on this. Because force is a vector quantity, we spoke about that in grade 10.
Yeah.
There must be direction.
Must be direction.
Yes, so this is what I'm going to do. I am going to choose. How is this object moving again? To the right.
Yes.
I will choose that right as positive. It means any force going to the left would be what? Negative. Okay, let's see something. What do you notice? Oh wait, there's a problem. There's a big problem before I even continue. There's a big problem. Let's sort this out quickly. Guys, before I continue. We spoke about this last week. We don't work with inclined forces. We only work with vertical and horizontal force. Please, that is so important. We work only with vertical and horizontal what? Do you remember we're finding the vertical and horizontal components somewhere? So if I look at this F is like this. Check the diagram. Do you see it? And there's an angle there. What's the angle? 20 degrees, right? Okay, so it's like this. We have a problem with that. F. What should we do? Vertical and? Now, do you notice this thing is up and right? So it means our horizontal will be right and our vertical will be what? Up. Do you remember that, right?
Yes, sir.
And this is called Fy. And this is called F what? X. Can I draw a new diagram quickly? Oh, time is running out. We had our normal, do you remember? We had our gravity. We had our tension.
Friction.
We had our friction. Now we have F. But now I'm not going to draw F again. I'm going to draw Fx and Fy. Make the circle what? Bigger. Fx, friction, tension, gravity. What's that one? Fn. And F what? Y. Please, that one we are not going to negotiate. You have to change everything to what? Vertical and horizontal. And we said something. We said we are choosing right as what?
As positive.
So it means this one is going to be what? Positive, negative, negative. Make sense?
Yes, sir.
Given? Make sense?
Yes, sir.
Positive. Please, you cannot do it without that. All right? Then we had our second diagram. Do we need to change anything on this second diagram? No. They are both vertical forces. Tension. Do you remember this diagram?
Yes.
All right. Guys, look at this diagram. I want to ask you a very simple question. I want you to think. The tension on the 2 kg, do you think it will be positive or negative?
Negative.
Negative. All right. Given, what do you think?
I think it's negative too.
All right. Why negative? Why do you think it's negative? My good learner.
It's facing down.
It's facing. No. The tension is not facing down. On the 2 kg. That's my tension on the 2 kg. Where's it going?
So it's going up.
All right. So look at this. We said right is positive, right? Left is what? Negative. So if I were to continue left, what do you notice?
Going down.
So left is the same as going where? Down. Up is the same as going where? Right. Does that make sense? Does that make sense to you?
Yes.
Up, it goes up here and it goes right there. It goes left here and it goes down. So check again. We said right as positive. Which one is going to the right? Do you notice this one is going up and then it will go to the right? Does that make sense to you?
Yeah.
It means my tension there will what? Positive. And my gravity would be negative. Please let me know if that makes sense to you guys. Let me know if that makes sense to you. Please respond. Did that make sense? Let me know. That's very important.
Yes, sir.
Mr. Given? Nzanga?
Yes, sir.
You sure, Given?
I'm sure.
All right. Guys, let's quickly answer the first question. What are the calculation question? What are we looking for? Tension in the string. And we can use F net equals to what? MA. But do you notice we don't even know this F? It's a problem. That's a big problem.
We have the mass and the acceleration.
Yes. Okay, let's try something on the 2 kg. I just want to show you something. I will stop here. We will do more of this next week. I don't want to rush you. I'm only going to do this part, just one question out of this. We will continue from here. Look at this. F net equals to MA. Guys, please, I want to explain something here. The 5 kg, how is it moving? It's moving horizontally this way. Please, I want you to listen to this part as I close. This one is moving what? Horizontally. What does that mean? Please listen to this. The 5 kg, if we understand this, calculation becomes very easy. Moves horizontally. I want to quickly tell you something. If I write two things, if I write F net is equal to MA, please watch. I will be using the horizontal forces. Are you with me there, everybody?
Yes, sir.
The object is moving horizontally. So when I say F net equals to MA, what will I be using? My horizontal what? Forces. Which means I will have Fx plus, remember net is adding, negative tension plus
Negative.
friction, and that will be equal to what? That's the first thing I want you to see. Please, did that make sense? I am only using horizontal, the one in the block. What then happens to my vertical forces? This I'm going to explore next week, please. My vertical forces are at equilibrium. That's point number 2. Vertical forces are at what? And what does that mean? How many forces are pointing up? It means forces up should be equal to what? With forces down. We did this last week. How many are acting up? 2. Normal force plus Fy should be equal to what? Please, this is very, very crucial. My object is moving horizontally. It simply means my horizontal forces are the ones that I'm going to use for F net. But my vertical forces, this is only on the 5 kg, please. Does this make sense? Given, are you with me?
Yes, sir.
Please, this statement is very important. 5 kg moves horizontally. So when I say F net, I am dealing with horizontal forces. My vertical forces are going to be what? At equilibrium. The one going up is the same as the one going where? Down. Let me round this up tonight by doing something now quickly. Still on the same question. Let us look at the 2 kg. How is the 2 kg moving? It's moving what? Upwards, which means verti. So when I say F net is equal to MA, which forces am I using here? These ones are going to be my vertical what? Please take note. If the object is moving horizontally, my F net will be horizontal forces. If the object is moving vertically, my F net will be what? Vertical forces. Let's write a formula for this and then we stop. What do you think my F net will be? On the 2 kg. Look at my 2 kg. How many forces do we have? 2. We just add T plus negative. Do you see where my signs are important? MA. What is positive times negative? Negative. What is FG, by the way? I gave you the formula for FG. Let me take you back. I'll take you back. Check there. Number 4. FG is M times what? G. So check here. Equals to what? M A. Do I know T? No. Do I know the mass? 2. Do I know G? It's a constant, 9,8. Do I know the mass? Do I know the acceleration? 2. Ah, Nana, why 5 kg? Oh, I get you. You see, it says, let me take you back quickly. We're going to finish now. Look at this. It says, let me show you something very important. Force F is applied on the 5 kg, right? And the system of blocks accelerate to the right. Both of them are going to move at the same acceleration. This one cannot be moving faster than this one. So both of them have an acceleration of what? 2. Do you notice we are done, my good learners? T minus 19,6 equals to 4. Move that 19,6 over, it becomes what? Positive. What's your answer? You are still using a calculator, Nana. Me, I'm done. Huh?
I'm tired.
You're tired. Alright, but guys, this is the introduction to Newton's laws. It's a bit complex, so I need you to first understand what I've done in terms of forces. We did Newton's first law, we did Newton's second law, we did all the forces, explained all the forces, free body diagram, and I'm trying to now show you how to do the I want to start from baby calculations. Remember, you are only working with vertical and horizontal what? Forces. Always give a direction. Choose the direction of motion as positive. Please, the plus and minus, you cannot succeed if you don't put plus and minus. Very, very important. Let's stop here. I know your head is now hot. It's about to explode. But it has been a simplified lesson so far. Take the note, read the note, this weekend, rewatch the lesson. This, I tell you, if you can send this video to a grade 12 learner, they'll be thanking you. Saying, whoa, thank you, because this is question 2 in grade 12. Ladies and gentlemen, please rewatch this lesson. It's our first lesson on, we covered a lot today. We covered a lot. Woo! Oh my word. Lesson 1 on Newton's laws is now done. Have a lovely evening, everybody. And we continue. Oh, shame, she's tired. We continue. Lesson 2. All right, Given. We'll talk on WhatsApp later. Good night, everybody, and goodbye.
Good night.
Good night.